Page 7 of Counting and Binomial Expansion Addendum. So in the first problem it says, give an example which demonstrates this equation here. And if you look at it, the pattern is that each one of these terms on the left, they have 5 chooses something, 6 chooses something, 5 chooses something, 6 chooses something, 5 chooses something, 6 chooses something. It's always 5 chooses something and 6 chooses something. On the right side, we have 11 chooses 4. Okay, what this reminds me of is one of those problems where you have like a group of men and women. Let's say you have 5 men and you have 6 women, and you are choosing members for a team. And let's say you have, so this is 11 people total. So if you're doing a problem where you're choosing out of 11 people, 4 people for a team, and it doesn't matter if it's a man or a woman, that you would calculate using 11 chooses 4, right? If you don't care if it's a man or a woman on the team, you could do 11 chooses 4 straight up. Now, if you wanted to break it down into, oh, what about the case where there are 0 men? What about the case where there's 1 man? What about the case where there's 2 men? What about the case where there's 3 men, etc.? So like, for example, this first case here looks like it's, okay, you got 5 men and you got 6 women. I want to know all the different ways to choose 0 men and 4 women, right? And if you did that, you would say, okay, 5 chooses 0 and 6 chooses 4, right? Then the next case would be, I want to know all the ways to choose 1 man and 3 women. So that would be 5 chooses 1 because there's 5 men and you're choosing 1 man from the 5 men. And 6 chooses 3 because you got 6 women and you're choosing 3 women out of the 6 women for your 4-person team. And so on. Okay? So that's the example that I'm thinking of. Okay? So you have instead of just doing 11 chooses 4, what you do is you break it down into the 5 men and 6 women, and you do each one separately, and you enumerate every single combination like I'm doing here. So 3 men, 1 woman, and the last case would be 4 men and 0 women. Okay, so that's the example that I'm thinking of, but you could do other things as long as you have like 2 subgroups of people within a main group. Okay, all right. 15. Line A contains 10 points, line B contains 7 points. If all the points on line A are joined to all the points on line B, determine the maximum number of points of intersection between the new lines constructed. Okay, so what we're going to do is I'm going to draw an example. So let's say, oh, I'm going to choose this point and this point on A, and then I'm going to choose like this point and this point on B, and then I'm going to connect them so that it forms 2 lines, and these 2 lines are going to intersect in a point. Okay, so you can see that by choosing any 2 points on A, any 2 points on B, you can always form an X with the 4 points that you chose that will have an intersection in between line A and line B. And so basically, how many intersections would you have between all the lines connected between A and all the lines connected between B? Basically, all you need to do is figure out, okay, how many ways can I choose 4 points, 2 on A and 2 on B, and that would be your answer. Okay, so let's do, how many different ways can I choose 2 points on A? That would be, let's see, there's 10 points on A, there's 7 points on B, so the number of ways I could choose 2 points from A would be 10 chooses 2, right? The number of ways I could choose 2 points from B would be 7 chooses 2. And then let's figure out what those 2 numbers are. So I could go to math, probability, and choose this C. And then here I'm going to put 10 chooses 2. And then I will also do 7 chooses 2. Okay. So I got 45 ways to choose 2 points from A, and I have 21 ways to choose 2 points from B. So you can see that like I could like multiply these together, because of the 45 ways I choose 2 points on A, I could also pair them in 21 different ways with the 2 that I choose from B. So it would be 45 times 21. So it would be 945 ways, 945 different intersections that I could form. And the one that I drew is just one of those examples. Okay? All right, now we go to 8G. And 8G, basically, we are going to do a bunch of binomial expansions that are a little bit more difficult than the binomial expansions that you did before. Let's take a look at number 11. Expand this trinomial to the 5th power in ascending powers of x as far as the term containing x to the 4th. So basically, this has terms up to probably x to the 10th, and they don't want you to expand the whole thing because that would take too long. So we're going to stop when we get to a power as large as x to the 4th. Now, if you look at this, you're like, okay, I know how to do binomial expansion. I do not know how to do trinomial expansion. So what you do is you actually group 2 of the terms to make a binomial. So you say, okay, so what I'm going to do is I'm going to treat this as a binomial expansion. One of the terms is going to be 1 plus 2x. I'm going to group it. Okay? So let's do that. If I group it like that, then I know that I have the coefficients for the number 5 row of Pascal's triangle. So I know that it would be 1, 5, 10, 10, 5, 1, okay? And I don't need to go that far because remember, we only need to pay attention to terms that are as high as x to the 4th and not higher than that. But so let's do this first. Now let's take the yellow part. We'll write it in orange. And so after the Pascal's triangle coefficients, we're going to put the A term here, 1 plus 2x to the 5th, 1 plus 2x to the 4th, and 1 plus 2x to the 3rd, right? And we can continue on with that if necessary. And then for negative x squared, we're going to put that to the 0, right? The first term is to the 0. And then the second term is to the first. And the third term would be negative x squared to the second. Okay. And in the next term, I would have negative x squared to the 3rd, right? So you can see that if I have negative x squared to the 3rd, that would be x to the 6th, right? If I have x to the 6th in this term, every single part of this term here is going to be x to the 4th or greater. And remember, well, actually it wouldn't be x to the 4th or greater, it would be x to the 6th or greater. So we definitely do not need this term here, because remember, we do not want to go beyond x to the 4th, okay? So maybe we have some terms in this term, but not all of them, okay? Now I'm just going to use green to do the next layer here. So here I could look at this and try to expand this. This part here, negative x squared to the 0 is just 1, right? So basically I have an expansion of 1 plus 2x to the 5th, and this is a binomial expansion, right? Now, although this is a binomial expansion, we do not need every single term from here, because eventually you're going to get to an x to the 5th term, and you don't need that one, right? What is this going to look like? It's going to look like 1, 5, 10, 10, 5, 1, right? And I'm going to write this one out. And then, so the 1 term, the A term at 1 is going to be 1 to the 5th, 1 to the 4th, 1 to the 3rd, and so it doesn't really affect the terms in the binomial expansion, right? So let's take a look at the B term, 2 to the x, right? So the first one is going to be 2 to the x to the 0, which does nothing, right? The next one is going to be 2 to the x to the first. The next one is going to be 2 to the x 2 squared. And the next one's going to be 2 to the x cubed. And the next one's going to be 2 to the x to the 4th. Okay? So basically the last term we don't want to look at because it would be 2 to the x to the 5th. And we know we don't want any of the 2 to the x to the 5th terms. Okay? Alright, now let's take a look at the next one here. So this would also be an expansion. It would be an expansion of 1 plus 2x to the 4th, which would have the coefficients 1, 4, 6, 4, 1. Okay, so we would basically have 1, 4, 6, 4, 1, and each one of the terms would be multiplied times 5 also. So that would be 1 times 5, 4 times 5, 6 times 5, 4 times 5, and 1 times 5. And then we would also have the b term for each one. So it would be 2 to the x to the 0. So we actually don't need that one. This would be 2x to the first. This would be 2x squared. This would be 2x cubed. Okay, and then we would have 2x to the 4th. I don't think we're going to be seeing some of these because look at this. We are also going to multiply every single term by negative x squared to the first. So let's see what that looks like. So we're going to do negative x squared, negative x squared. Do you see how this is already x cubed? Negative x squared. And do you see how this one is already x to the 4th, right? So we don't want to go past here, but let's see, negative x to the negative x squared here, and then we're already above x to the 4th. So we don't want this one. We don't want this one because the degrees are too high. Okay? So we basically have this one, which is negative 5x squared. We have this one, which is negative 40x cubed. Negative 40x cubed. And here we have negative, this would be 30 times 4, which is negative 120, right? This would be 2 squared, which is 4 times 30, and then x to the 4th. Okay. And then, last of all, let's take a look at this term here. This would be cubed, so that would be 1, 3, 3, 1 would be the Pascal's triangle coefficients, 1, 3, 3, 1. And the first term would be, each one of these terms would be times 10, times 10, times 10. Each one of these terms would be times x to the negative x squared squared, which would be x to the 4th. Okay, so actually most of these terms are already going to be like too high degree, right? Because when you have this, you're going to have x to the 4th, and we don't want to go any higher than x to the 4th. So let's take a look at just the first term and see what it looks like. So we're going to expand 1 plus 2x to the cubed. The a value is 1, so it doesn't really do anything. The b value is 2x, so the first term is going to be 2x to the 0, so there's nothing there. We're just going to multiply it times 10, and we're going to multiply it times x to the 4th, because each term is multiplied 10 times 10 and x to the 4th. And then the next term is going to be times 10 and x to the 4th. It's also going to be times 2x, because the b term is going to be to the first power here, and so this is already going to be too big, and this one's going to be too big, and this one's going to be too big. So what you're left with is this term, this term, this term, this term, this term, this term, and this term, this term, this term. Okay, so let's, I'm going to write all those in blue. So first I'm going to say, okay, what are the constant terms? So I got 1, and that's the only constant term. And then I'm going to do the x terms, the x to the first term, that's just this one, right? So I'm going to put 10x. And then the x squared terms, I'm going to have this one, and I'm going to have this one, and I think that's it. So this one here is basically 40x squared, right? 40x squared. And this one here is negative 5x squared. So that would be 40 minus 5, it's 35x squared. Okay. And then now I'm going to look for the x cubed term. There's this one, and there is this one. So this is basically 80x cubed, and this one here is negative 40x cubed. So we're left with 80 minus 40, which is 40x cubed. And then finally, I got this one and this one for x to the fourth. And then I also have this one here. So basically that's, this one here is 80x to the fourth. This one here is plus 10x to the fourth, so that would be 90x to the fourth. And then I would subtract 120x to the fourth, so that would be negative 30x to the fourth. And then it would continue on with degrees that are higher order than x to the fourth, so we wouldn't need those. Okay, so that is definitely a binomial expansion problem worthy of HL. You can see that all you needed was the binomial expansion rules, but by putting in a trinomial instead of a binomial, they made it quite complicated. And to optimize your work, you need to be super aware of which terms are going to have x to the fourth or higher degree variables in them, so you can discard them. So that was pretty challenging. This binomial expansion problem also is a little bit difficult because it's not just a straightforward numbers problem. They just give you an expression and then they ask you to prove this thing, which you look at it and you're like, what are they talking about? Well, if you look at this expression, one thing that you're going to notice is that it has n chooses 0, n chooses 1, n chooses 2, n chooses 3, and it goes up to n chooses n. And that basically is describing the Pascal's triangle expansion for n equal, for the degree n. So you think, okay, so basically what they want me to do is they want to expand this using the binomial expansion. So basically, the coefficients in that case are going to be n0, n1, n2, etc., right? n3, and so on, all the way up to nn, right? And then the only other thing, since the a value is 1, the a value doesn't really affect the terms. The b value is x, so in the case of the first term, x to the 0 is just 1. The second term would be x to the first, second term would be x squared, third term, this term would be x cubed, and then the last term would be x to the n, right? Now, the fact that they have negative 1 to the n here instead of x to the n makes me think, okay, what they want me to do is they want me to substitute in x equals negative 1. Now, why would I do that? Well, if you look at the original expression, it's 1 plus x to the n, right? So if I put negative 1 in for x, what happens? I have 1 minus 1, which is 0, which is equal to 0 to the n, which is equal to 0, right? So basically what they want me to do is they want me to substitute in x equals negative 1 and show that this complicated expression here with all these combinations in it is going to sum up to be 0, okay? And the reason why I know that is because 1 minus 1, the n power is 0, okay? So go ahead and do that. So we'll say, okay, x is equal to negative 1. Let's see what happens. So the first few terms, it's going to be n0. These are all plus, by the way. N0 minus n1. And why would it be minus n1? Because if you put negative 1 in for x, you're going to have negative n chooses 1, right? And the x term goes away. The x variable goes away because you've substituted in negative 1. The next term is going to be n chooses 2, and then x squared is negative 1 times negative 1, which is positive 1, so the x kind of disappears also, and you're just left with plus here. The next term is going to be minus n chooses 3, And x cubed becomes negative 1 times itself 3 times, which would be a negative 1, so that's why you would get a negative here. Okay? And then we could say dot, 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 plus, and we'll put the last term, which would be n times negative 1 to the nth power. And we could say that that is equal to 1, because if x was negative 1, then basically this expression here is 1 minus 1, which is 0 to the n, and that would definitely be 0. Okay? So, we have done the expansion, and we've shown that this expansion is equal to 0. Okay? All right. And next video will be page 8.